Hi everyone, it's Mr. Baker here with another physics video. Today we're going to be looking at radioactive decay. Okay, so we're going to be looking at radioactive decay today, and we're going to be answering these questions. Why are some things radioactive? And does radioactive stuff really glow? So to understand radioactive decay, we've got to look at a few other things first of all. So we've got to understand what something called isotopes are. So I've got some pictures here of some isotopes of a hydrogen atom. And isotopes are the same type of element, and so they have the same number of protons and electrons, but they've got a different number of neutrons. So you can see here I've got three isotopes, all of hydrogen, and in the first one, this is the hydrogen that we know. It's got one proton, and that's what hydrogen is. In the second example here, I've got deuterium, and that has got one proton and one neutron. So that is an isotope of hydrogen because it's got a neutron as well as the proton. And then you can see in the third example, tritium, we've got a proton, so it's still hydrogen, but it's also got two neutrons. And this one here is unstable, it's radioactive. So unstable isotopes break down, and we call these types of isotopes radioisotopes, like radioactive isotopes. An unstable isotope is one that has different numbers of neutrons compared to the number of protons. So radiation is given out to try and balance this out. And there are three types of radiation that try and do this. It's alpha, beta, and gamma, or as alpha, beta, and gamma are given off, it makes the unstable isotopes more stable. So we know, hopefully now, what an isotope is. Something else that you might have seen in your chemistry lessons is we also need to know about, so that's the atomic notation. So in atomic notation, you've hopefully seen this before. So you've seen like the big X there, that would be the element, so that might be H for hydrogen, or it might be a big C for carbon, whatever it might be. So that would be the symbol for the element. And then we've got the mass number and the atomic number. So the mass number is on the top left, and we use the symbol, a little a, for that one. And the mass number is the number of protons plus the number of neutrons. So that's the total stuff that's inside the nucleus of the atom. And then the atomic number is just the number of protons. And we use these two symbols, A and Z, for this. Now A stands for Atomgewicht, and that literally means atom weight in German. So that's the mass number. And again in German, the Z stands for Atomzahl, and that means number. Zahl means number, and so that means atom number. So that's the atomic number. So the atomic number, you might also say the proton number, because it literally is the number of protons. And then obviously in an atom, that would also be equal to the number of electrons. But when we're looking at radioactive decay, we're really just looking at the nucleus of the atom. That's what we're interested in. Okay, so we've looked at some background stuff, the stuff that we need to know before we look at radioactive decay. So let's have a look at what type of radioactive decay actually happens. So we've said that there are three different types, and the first one we'll look at is alpha decay. Alpha decay generally occurs when a large nucleus is unstable because it's got too many protons. So in this animation, I'm going to show you, we've got a large atom here. You can see lots of protons and lots of neutrons. So the red ones are the protons in my diagram here, and the blue ones are the neutrons. And so in alpha decay gives off two protons and two neutrons like that, which is the same as a helium nucleus. So an alpha particle is the same as a helium nucleus, and then it gives it off, and so this nucleus here has become more stable because it's lost two protons and two neutrons. Okay, so that's alpha decay. Let's have a look at how we could represent that with that notation we just looked at. So we've said that an alpha particle is the same as a helium nucleus, and it contains two protons and two neutrons. When an atom's nucleus decays and releases an alpha particle, it loses two protons and two neutrons then. So this might be a typical kind of equation that you might see. So we've got a uranium atom there, so uranium-238, so the 238 is the mass, so that's the number of neutrons plus protons, and we've got the proton number is 92. So I know, or the atomic number is 92, so I know that that's the number of protons. And then you can see that that turns into thorium, so it's a different element, because on the right hand side there you can see this alpha particle has been given off. So that symbol there that kind of looks like an A is the alpha symbol for an alpha particle. And you can see that its mass number is 4. It's got 2 protons and 2 neutrons. And the atomic number then of the alpha particle is 2 because it's got 2 protons. So the mass number of the uranium has gone down by 4. It's gone from 238 to 234. And the atomic number has gone down by 2. It's gone from 92 to 90. So what you've got to be able to do is to balance this out, and so this is how we know what's on the left-hand side of the arrow and what's on the right-hand side, because the numbers will equal the same. So on the left-hand side, we've got the mass number is 238, so everything on the right must equal 238. So my thorium atom has got a mass of 234, and add that to the mass of the alpha particle, which is 4. 234 plus 4 equals 238. And the same thing for the proton number or the atomic number. The atomic number of the uranium is 92, the atomic number of the thorium is 90, and the atomic number of the alpha particle is 2. So on the right hand side of the arrow, 90 plus 2 equals 92, which is what the uranium's atomic number is. So kind of question is what you might not have the alpha particle, might show it as like a big X or something like that, and say, what do you think this is? And the way you would know it is because you know that those numbers must balance out, and you know that an alpha particle has got 2 protons and 2 neutrons, and that would balance off that equation. Okay, so since the number of protons has changed, the uranium atom has decayed into a new element of thorium in this example. Let's have a look at what's happening inside beta decay. So beta decay happens when the nucleus is unstable because it has more neutrons than protons. So let's have a look at the animation of this one. So we said the blue ones are neutrons and the red ones are protons. So look, when I change what's happening here, we've got blue neutron at the top, turns into a red proton and a yellow electron. So let's look at that again. The neutron turns into a proton and an electron. Now that electron gets ejected as a high energy beta particle. So in beta decay, a neutron turns into a proton and an electron, and that electron is ejected as a beta particle. Okay, so let's have a look at that in terms of the notation then. So during the decay of a nucleus, a beta particle may be emitted. A beta particle is the same as a high energy electron. When an atom's nucleus decays and releases a beta particle, a neutron turns into a proton, which stays in the nucleus and emits a high energy electron. So this would be the kind of equation that you would have then. So we've got carbon on the left-hand side. It's carbon 14. Normally we have carbon 12, which is stable, but here we've got carbon 14. So it's an isotope, a radioisotope of carbon. It's an unstable isotope. And you can see it's unstable because it's got 6 protons. I know that because the atomic number is 6, so it must have 6 protons. And it must have 8 neutrons because 6 plus 8 equals 14. And that's obviously not the same number. 6 and 8 are different numbers. We really want to have the same number to make it stable, and so this is unstable. So carbon 12, which has got 6 protons and 6 neutrons, is stable, but here carbon 14 is unstable. And then so you can see on the right hand side we've got a nitrogen atom that has been turned into, and then also the beta particle on the right hand side. So what's happening? So the mass number here has stayed the same. So the mass number has stayed the same, and the beta particle has got a mass of 0. Now that's because what we do is we're comparing, we're looking at the relative masses of things, and protons and neutrons have basically got the same mass. So we say that they've got a relative mass of 1, but a beta particle has got a really, really small mass and a pretty much negligible mass compared to a proton and a neutron. So we can say that the mass is 0. So the mass there has stayed the same overall. So if we were to look at the mass of the right hand side and the mass of the left hand side of our equation, then they would be the same. And on the what's happening underneath to our protons then, so the atomic number has gone up by 1. So that must mean that I've gained a proton. So a neutron has turned into a proton. And I know that a neutron has turned into a proton because the proton number has gone up by 1, but the mass number has stayed the same. So now I've got 1 less neutron and 1 more proton. So initially, in my carbon-14 there, I had 6 protons and 8 neutrons. On the right-hand side of the equation, my nitrogen atom has got 7 protons and 7 neutrons. So the proton number has gone up by 1, and the neutron number has gone down by 1. But overall, the mass number stays the same. At the moment, the proton number, the atomic number, has gone up by 1. So the charge, because the charge of a proton is positive 1, I need to balance that out somehow. And so that's why we've got this negative 1 on the on the beta. And that's why we've got this negative 1 on the beta particle. The negative 1 shows that it's got a charge of -1. And so now I can balance out the right-hand side of my equation, because 7 minus 1 equals 6 as well. So I know that I've got a beta particle here because the mass has stayed the same. The atomic number has gone up by 1. And so I know that I must have something that balances that out, a beta particle which has got 0 mass and it's got a charge of -1. So the decayed atom has gained a proton and so has become a new element. Right, so you don't need to be able to necessarily look at the equations of gamma radiation, but you do need to know what it is. So let's have a look at the animation. So here we've got a nucleus which is wiggling about, it's got too much energy, and it gives off gamma radiation. And that's basically what gamma radiation is. Gamma radiation occurs because a nucleus is oscillating about, and to make that stable, gamma radiation is given off. There's excess energy given off, and that energy then is away from the nucleus, and the nucleus is no longer wiggling about because it's given off that gamma radiation. Okay, so that's our 3 different types of radioactive decay, and that's basically the end of the lesson. So you should be able to use nuclear notation to identify the type of decay taking place from a nuclear equation and describe what an isotope is. You should be able to calculate the number of neutrons and protons in an isotope by using nuclear notation and describe the differences between isotopes. And you should be able to complete decay equations for alpha and beta decay. Okay, so we started off the lesson by asking these questions. Why are some things radioactive? And does all radioactive stuff glow? Well, some things are radioactive if they contain unstable isotopes or radioisotopes. Unstable isotopes may decay to become more stable, and they are said to be radioactive and give off alpha, beta, or gamma radiation. Some objects, like specialist glassware and some watch faces, used to contain small amounts of uranium to enable them to glow in the dark. They only had about 2% uranium in them, so barely registered above the background radiation when measured, but they still added to the excess exposure of radiation that somebody might get. Radioactive materials don't really glow. What they do is they fluoresce. Watch faces and that glassware, they absorb ultraviolet light and then they re-emit it as visible green light, which makes them look like they glow. Okay, so that's been all about radioactive decay, and I've been Mr. Baker, and this has been another physics video, and I will see you next time. Thanks very much.